Welcome to the flock. Let's dive into the combined gas law with a problem that's applying the new volume of a bag of potato chips at a different elevation. But before we can solve it, what is it? Basically, the combined gas law is just taking Boyle's law, Charles' law, and Gay-Lussac's law and mashing them all together into one equation. This way we have pressure, volume, and temperature all accounted for. The great part about this equation is that you can use it for any problem that would require Boyle's law, Charles' law, or Gay-Lussac's law. So essentially, the combined gas law can replace all three of those laws. So check it out. In Boyle's law, we know that there's a pressure times a volume. When we look at Charles' law, we know that there's volume divided by temperature. And in Gay-Lussac's law, we see pressure divided by temperature. So if we were to combine all of these concepts together, the P and the V on top would be multiplied, just like Boyle's law, and that would have to be divided by temperature, since that's also what's happening in both Charles' law and Gay-Lussac's law. So what we end up with is an equation that looks like this, the combined gas law equation, where we have our initial pressure times our initial volume divided by our initial temperature in Kelvin. That still applies here. And we're setting that equal to our final pressure times our final volume divided by our final temperature, again in Kelvin units. So now, let's go ahead and solve that combined gas law problem about potato chips. We have a bag of potato chips packaged at sea level and has a volume of 315 milliliters at 25 degrees Celsius. So already we're seeing that there's a pressure value that could be gleaned from this because it's saying sea level, so we know that the pressure is 1 atm at sea level. And we're also seeing a volume and a temperature. If this hypothetical bag of potato chips was transported then to Denver at a new pressure of 0.77 atm, so less pressure, higher elevation, what will the new volume of the bag be in Denver at 10 degrees Celsius, because it's colder in Denver. So we have another T value there, and we're trying to find a V value. Let's fill in our blanks then. All right, remember that our temperatures have to be in Kelvin. So what you can see that I've done here is I've taken my degrees and I've added 273 to each of them to end up with a value of 298 Kelvin for our temperature 1 and 283 Kelvin for our temperature 2. Now all that's left to do is plug and chug into our combined gas law equation. Let's focus on the left side of the equation first. 1 times 315 is just 315, divided by 298K is 1.057. And now that's still going to be set equal to 0.775x over 283. The objective here is to get x alone, so we need to get rid of the denominator. In order to do that, we need to multiply both sides by 283. And now I end up with 299 on the left side, 0.144, set equal to 0.775x. And now in order to get x alone, we just have to divide off the 0.775 from both sides. And now we can see that our x value, our V2, is going to be equal to 385.99. Now what units go on this? This is a volume, and our initial volume had milliliter units. Therefore, our final volume is also currently in units of milliliters. Since I didn't specify whether I wanted it in liters or milliliters, this is okay to do. Let's try and check our understanding on this just briefly here. Our pressure, we know, went down, so we had a pressure decreasing. We know from Boyle's law that if pressure decreases, the volume should increase. But what I found is really confusing for students is that, okay, yeah, that worked with the Boyle's law understanding, but what about the temperature? The temperature went down. And if temperature goes down, according to Charles' law, the volume should also go down. But in this case, our volume went up like it did in Boyle's law. Okay, so the rationale for this is that it's the combined gas law, so it's taking all of those variables into account. In this case, the pressure difference mattered more than the change in temperature in terms of how the volume was affected in the bag of potato chips. So just because the temperature went down doesn't mean that the volume had to go down as well, according to Charles' law, because the pressure variable actually superseded the temperature change and thereby caused the volume to actually go up. Let's see the combined gas law in action by putting an egg in a bottle. While you watch the demonstration, think about the atoms and the molecules of gas, the pressure, the volume, and the temperature, and how these could all relate to the combined gas law. We're gonna get this egg in this Erlenmeyer flask using a little bit of chemistry. There are gas molecules inside this Erlenmeyer flask. We're going to increase the temperature by lighting a piece of paper on fire and putting it inside the flask. Now we're going to put the egg over the top. Watch the top here. As the pressure changes, the egg is going to slowly get sucked into the Erlenmeyer flask. Ta-da! So what happened here altogether? We had gases in here. We increased the temperature by lighting the paper on fire, and thus the gases moved faster. And as they moved faster, they collide with the walls of the container that isn't moving more often. When they collide more often, the pressure goes up. If you noticed at the lip of the flask, the egg did this little bouncy dance, releasing some of the gas molecules as well. That means there was a change in volume. The volume went down, the pressure went up due to the increased temperature. And then, when the flame extinguished, the temperature went down, the pressure went down, because now the gas is moving slower, and the volume was still less than it initially was since some gas escaped, creating the perfect situation for the egg to be affected by gravity and pull it gently into the flask, thus representing the combined gas law. And that's how you get an egg in a bottle. How do you get it out? Well, if you just get the egg to the nozzle of the bottle and hold it over and hold this end over some boiling water, the opposite's true. The temperature will increase for the gas molecules trapped in here and gently force the egg out the other side. Now that you've seen me do a calculation, go ahead and give this one a try all on your own. Pause the video now. All right, hopefully this is the pressure 2 value you came up with, the 0.8758 ATMs, which makes sense because as you go higher in elevation in an airplane, the pressure does in fact drop. They do try to equilibrate that though by adding extra oxygen to the actual airline cabin, but you can always tell that you're increasing elevation and decreasing pressure because your ears get all plugged and funky. Let's try one more practice problem. Go ahead and pause the video here and see if you can solve this scuba diving the bends gas law question. So if you've ever scuba dived before, this can be a deadly condition thanks to those very small nitrogen bubbles in your bloodstream and the pressure differences from going underwater back to the surface. That's why you never want to rise too quickly if you're scuba diving. Let's check your answer, shall we? All right, so hopefully you came up with a volume 2 of 191.86 milliliters. Holy Toledo, that is a huge expansion of nitrogen bubbles in the bloodstream. This would definitely kill you. And this is the reason why if you're scuba diving, rise slowly. Before moving on to the next gas law, make sure that you test yourself on the combined gas law first. See if you can answer this problem about traumatic blood loss. In this lesson, we combine Boyle's, Charles, and Gay-Lussac's law to make the literal combined gas law, which relates pressure, volume, and temperature all together in one mathematical expression. Make sure you're keeping track of your units. If you're calculating with volumes of milliliters, your final volume will also be in milliliters. Make sure all your units match, and make sure your temperatures are in units of Kelvin. Please give this video a quacks up and subscribe to Duckonta for some more free educational content. Hope your day is just ducky.
No ducks, no glory.